My name is Mark Ryland. I'm a solutions architect with Amazon Web Services. I work in the public sector team. So we facilitate the use of Amazon's web services technology in federal, state, local education customer base. Very excited to be here to give a talk about primarily focused on Virtual Private Cloud, which is our networking isolation technology, which we're advancing and encouraging people to use. How many people here are currently Amazon customers, Amazon Web Service customers? Whoa, look at that. Awesome. How many are using VPC? Only a small number, OK. Well, over the next year or two, I think pretty much all the hands will be going up as we enhance the capabilities of VPC. So this first part of this talk will be a little bit of a review for those who are currently using EC2 classic networking. So bear with us on that, to kind of get everybody up to speed and talk about a few little subtleties, perhaps, that even the current users maybe had not thought fully through. And then we'll talk about both the power and the limitation of the current networking technology, and then introduce VPC. We'll go through that. So this is essentially our outline. Review of EC2 networking. We're going to do some demos along the way. How many people are tired of PowerPoints all day? Raise your hand if you're tired of PowerPoint. OK, so we're going to do some demos. Now, I have a confession to make. I came in here last night to practice my demos, and the networking was so bad that I went home and I videoed them. I screencasted them. So I apologize for that. I just couldn't, it's risky enough to do live demos, and when you have bad networking, it was just a little too much. However, there's one demo that involves audience participation. So this will be exciting. Anybody that's got a laptop and is willing to do something, you're going to actually be able to participate in one of these demos. So that part will be live. So as I said, EC2 review, look at VPC, the key concepts, new capabilities, and the common use cases. Talk very briefly at the end about DirectConnect, which is a kind of companion technology for VPC. And then we'll have time for questions and answers at the end. All right, so let's get moving here. So EC2 networking, we all know and love. It has a lot of powerful capabilities, and it has some quirky elements to it as well. Every instance has essentially its own private address and its own public address. And the lifetime of these addresses essentially is tied to the instance running. So if you stop an instance and restart it, you'll end up with a different address, both public and private, in the normal case. This is a one-to-one NATed environment, so your instance will see a private address in the 10.0/24 range. But as it goes out onto the internet, it will manifest, of course, a public address. Very important to grasp, and maybe it's obvious to everyone, but just to level set. Often when we talk about NATing in networks, we're talking about one-to-many NATing, where you have a set of private addresses behind a single node, which manifests a single public IP to the world. That type of NATing is more strictly should be called NAT-PAT, because it's a network address translation. You rewrite the addresses as they go through, and you also write the ports. And it's the port rewriting which enables the one public address to manifest the behavior of many private addresses. EC2 networking does not do port address translation. It's a one-to-one NAT, which means that the only rewriting is of the destination address or the reply address as you go out. And so the port values stay the same, and that means there's lots of software that is just completely fine with that, and there's no issues. There's another important element of this, which is we call split brain. People call split brain DNS. That is, if you use the DNS name of one of these instances, you'll see different behavior depending on whether you try to reach the instance from inside the EC2 network or outside. The right thing will happen, but it's slightly different. We'll show that in a second. The core value proposition of EC2 networking today is the security group model. Security groups are very powerful, very flexible. We'll talk about those. It provides essentially the current way that you can get the behavior you want in terms of controlling access to your instances. The kinds of things you would on premises do with maybe subnetting, things like that, you can typically do with security groups. It's a very rich model. Security groups themselves are hypervisor enforced firewall rules. That's one way to think about them. So independent of your operating system settings in EC2, prior to any packets reaching an operating system, the rules that you write in your security groups are going to be enforced. Very, very key concept. It's also important to note, though, that you can also think of them as sort of objects in a networking database, a management database, because if you change those rules, then those changes will be propagated to all your instances that have that security group associated with them. So it's a very powerful and flexible tool. And when you write, and you can use the security groups as one of the values in the rules that you write. So in addition to writing rules like you're used to with subnets and CIDR blocks and so forth, and ports, ranges, you can also use security groups as a value in a security group rule so that you can write rules very easily that say, for example, all the instances that have this security group can only access instances that have this one or vice versa. And we'll see that in a quick demonstration in a second. And finally, a very important element of classic EC2 networking is the elastic IP. Everybody knows what an elastic IP is, right? That's the ability to have a public IP whose lifetime is not tied to a particular instance, but essentially sits around, again, as an object, as a resource, which you then associate with your instances. So let's give an illustration of some of these concepts we just went through. Essentially now we have in our different availability zones the different sets of customers. And the customers will bring up their instances and they'll see different addresses on those instances. So when you look at the operating system checks to see what its address is, it'll see a set of addresses in this kind of general pool of private addresses. Now these, again, I want to emphasize, by default, these are isolated from one another. The hypervisors conspire to make sure that the security group rules are enforced, and the security group rules will normally, unless you change them, keep all packets contained within a single tenancy. So your packets will flow to your instances. They'll never flow to others. There's no exceptions to the security group rules. It doesn't matter whether your placement happens to be on the same piece of physical hardware or a different piece of physical hardware. There's no shortcuts in terms of the enforcement. So your isolation will remain constant across all the different possible placements of a virtual machine in EC2. Now, for each of those instances, you'll also receive an IP address, a public IP address. You can think of it as being at the edge of the edge of the border network, which is a part of this cloud environment. And when your instances go out to the outside world will see these addresses, which have been rewritten by the NAT devices at the edge of the network. And on the return, the rewriting happens the other way, so your instances will see their own addresses as the destination of the return packets. Or vice versa if your instance is acting as the server. Now let's go ahead and just demonstrate some of these concepts. Very simply, I've got a couple of servers running in EC2. I'm using Windows servers because it makes it a little bit easier to show visually what's going on. So I've got server A and server B. They have public DNS names. One of them has an elastic IP. The other one does not. They both, as normal, have private IP addresses. They both have public addresses as well, but only the elastic IP shows up because the other public addresses, you can think of it as more ephemeral. So this is my machine with the elastic IP. It's got the red command prompt, blue command prompt. You can see what the local machine sees when you do an IP config. You'll see that local address. Now, here's what's interesting. First of all, we've got wide open security groups at this point. So this is absolutely not security best practices. I'm starting off with open systems, and I'll begin to shut them down. So I can ping from one EC2 instance to another, and you'll see the expected behaviors. If you trace route using the public DNS, if you look at that first trace route, you'll see it goes directly to the private address. Now let's do a different trace route. Let's trace route from an EC2 instance to the public IP of the other EC2 instance. And you'll notice a little bit more complexity to the route. So what's happening is my networking system, our networking system is doing what it's told to do, which is to go to the edge of the network. And there's some delays here because the reverse DNS lookups are failing on some instances and so forth, and some are not replying to the little trick which trace route. People know how trace route works. I've been told this is a Google interview question. Each packet gets a time to live of 1 for the first, then 2, and so forth. So basically, these devices are sending you back packets whose time to live is expired. And that's the trick. So what's happening now is you can see the more complicated trace route when you use the public address. Now I'm going to start something else. I'm going to start pinging these instances and start showing the behavior of security groups. So on the left side of the screen, the red command prompt is pinging one instance, the blue and the other. And inside EC2, the two instances are going to ping each other. So they're pinging across. So now here's my wide open security group. It's got all ICMP traffic flowing. It's got all TCP traffic and all UDP. So let's first of all, let's get rid of this ICMP traffic, especially from the outside world. That's kind of very dangerous. So we're going to shut that down. I'm going to make it so that only traffic from the same security group, that namely this is so self-referential, is going to be able to ping. So now when I look at the pings coming from the outside world, namely my workstation sitting outside the cloud, my pings begin to time out. Inside the cloud, the pings continue, because now I've restricted them. I've locked them down to being within the common security group. Now, let's get a little more restrictive. Let's get rid of ICMP traffic altogether. Force that rule. Now we'll go back and look at the behaviors of the two internal systems inside the cloud, and you'll begin to see that the ping traffic now is being rejected by the network. So now we've got a bit more of a lockdown environment. So let's go and now be even more realistic, and let's close down the traffic. By the way, there's simple websites. Phony little websites on those two servers. So I'm going to update them from outside and inside, and you can see if you look at the we'll allow port 80 traffic on those instances, only from inside, so only the security groups. Now I'm going to update that, and you'll see my Firefox little spinning circle, which means things aren't happy. When I go inside the cloud, I go to click to update. It should work fine, and then I realize, wait a second, my RDP session has failed because I just shut off port 3389. So I hurriedly go back, fix the little bug there so that make the demo continue to work. RDP is timing out, but it will reconnect. It's one of its characteristics is to do retries. Boom, the retries works, and now I've got access to those machines again. So now my very artificial little world in which I've locked down everything except at a critically important port to lock down, 3389. The web pages are timing out from outside. They work inside. So there's just a basic illustration of some of the concepts. So very powerful, flexible system with some limitations. One limitation is ingress-only control. So in terms of your network isolation and control, there's a bit of a limit. You might want to limit egress from your instances as well. There's rich dynamism in terms of the content of these security groups. You can rewrite the rules. Those rewrites get propagated very quickly, so you have rich control. However, you can't change the security groups in the lifetime of an instance, so they're kind of bound to instance life cycles, and that may be something that you would like to have more control over. The really, in some ways, biggest limitation is not so much a limitation of the technology, but it's a limitation of the mindset, of the mental model for EC2. Because in a way, we're at war with the way we're accustomed to using networks on premises. And on-premises networks and internet in the wild type networks, we're accustomed to thinking in terms of subnets and ACLing subnets and having the ability to control routes and all those kinds of things that just aren't present in the current classic EC2 network. You can't create these little private enclaves. You might want to set up the equivalent of a demilitarized zone type network, which you are accustomed to doing on premises. Again, you can use security groups to do a lot of these exact same capabilities, and people do this on a daily basis, and EC2 networking is by no means problematic. It's a very, very successful environment. But people want more richness, and we want to be able to provide that. So we'll talk about how VPC is able to improve the situation a bit, give you more choices and more flexibility. One of the things, though, that is a kind of real limitation is a lot of software is really unhappy with totally dynamic addressing. So an Active Directory instance, for example, does not like having its IP address changed. or lots of other types of devices and systems are like that, lots of software. Some software gets confused by the NATed network when the external IP address is not the same as the internal. Again, most software is fine with that. Some software is not. There's also things like virtual appliances that really want to have the ability to have fixed IPs, things like perhaps multiple IPs per interface, to be able to multi-home so that there are two logical connections. Many security type appliances are very fixed model about how they like to be networked. All those kinds of things are difficult or impossible to do in traditional EC2 networking. So let's talk about VPC. So VPC is a user-defined virtual private networking for EC2. You can create completely private enclaves within the cloud. You can have mixed private-public. You have much more control over ingress and egress and much more flexibility about things like routing. Security groups have more richness. ACLing on subnets, all these are new capabilities which you can take advantage of if you want to. And really, as I mentioned earlier, one of the key value propositions for VPC is that it reuses a lot of knowledge that you probably already have because you're already accustomed to working with subnets, subnet routes, ACLs on subnets, things like that. So let's look at the capabilities in a nutshell, then we'll explore these in a bit more depth as we go along here. First of all, you have the ability now, and as time goes by, some of these precise things I'm about to say will probably change and get more flexible, but right now you are able to create a address space or an enclave of up to a /16 in CIDR. Everybody know what CIDR notation is? Classless internet domain routing. If you don't worry too much about it. But basically, it's just a way to designate address spaces. Within that CIDR block, you can then create multiple subnets. There's a soft limit of 20. If you need more, you can contact us. There's a form on the website. But that usually suffices for most purposes. Those subnets can be as large as a /16, so you can take a VPC and make it one big subnet if you want to. And there might be reasons to do that. Very typical usage pattern is to make a bunch of /24s inside. It's just visually easier to see which is the numbering of the subnets because of the octets. 24s are kind of easy to understand. So that's a very common use case would be to create a bunch of /24s, but if that's too small, you can create anything from, again, a /17 all the way down to, I can't remember what the limit is, but it's like a /28 or 29, something like that. So you have this ability to create this private enclave, an addressing enclave, and the subnets within that. And then on top of that, you begin to define a set of capabilities that, again, are analogous to what you're used to for on-premises networking. So you have route tables. You have DHCP servers, virtual DHCP servers. Those are configurable, customizable. You can have different DHCP servers for your different VPCs. Again, virtual ones, where the environment itself is manifesting these addresses to the requesting devices. You can spin up a NAT instance, a NAT-PAT instance now. Let's to be precise. As I said earlier, I said we got to be more precise now. So this will be a port network address translation, port address translation instance, so that your instances that want to go out on the internet can do so from behind a single IP address. And there's a built-in capability for standing up NAT instances and then creating an internet route which goes out to that particular instance. And in addition, there are these important kind of virtual concepts of the internet gateway, which really maps to your elastic IPs. Elastic IPs are still available, so you can take any given instance so long as it has an internet gateway, which is a virtual object in the environment. As long as one of those is associated with the subnet of that instance, you can slap an elastic IP on that instance. So now you're right back to a similar environment to what you were used to in EC2 networking, traditional EC2 networking. You can have completely private subnets where there's no internet access at all. And furthermore, you can set up customer gateways and VPN tunnels so that, in effect, this entire private enclave that's sitting in the public cloud, from a networking and addressing perspective, is entirely private, and through the VPN tunnel, connects directly to an on-premises network, and it just as a normal routed extension to your on-premises network. So you can set up the addressing such that there's nothing tricky going on except just extending your on-premises network into the cloud. Some other nice capabilities. The private IP addresses, first of all, any given instance, you can assign a particular IP address to it. It's associated with the lifetime of the instance, so it's going to be stable over the lifetime of the instance. There's also a very interesting and cool capability, which is we call elastic network interfaces. So your instances can now be multi-homed on 2 subnets using another virtual network card that gets associated with your instance. We'll show a demonstration of that in a moment. These ENIs, elastic network interfaces, they're sort of objects in this virtual world. You can create them, assign an address to them, assign a security groups to them, even assign an EIP to them. And they can sit there ready to go until you need them. And then you dynamically bind them to a running instance. The instance does a little magic. With Windows, it's plug and play. With Linux, you do a little mount command. And suddenly you've got a second network interface with all those pre-assigned attributes. You can then unbind the ENI if you want to, and assign it to another instance if you want to. And all of the networking properties will flow with the ENI. The only limitation is they stay within the same subnet. Okay, that would be mind-blowing to try to figure out how one of these things would change subnets, because they have all these properties that are address relative. But within a given subnet, they become essentially networking objects that you can use in different instances to do some really interesting things, and we'll demo some of that. One of the use cases that we've seen right out the gate when we provided this capability was, we call it poor man's high availability. So you can actually have an instance that's doing work, keep a little task going, checking to see make sure it's healthy, make sure it's healthy. If you see a health problem with that instance, the little monitoring app can call an API, unbind the interface, stick it onto another instance, which is ready backup, ready to do the same work that the first instance was doing. So you can basically, now all the traffic flow will go instantly. Well, instantly, there's probably a couple second delay. You'll lose a few packets. But if everybody's doing retries, like good internet-style applications, you got to do a few retries, because we all know that networks have failures and are lossy. Then the work will just continue. So it's a very nice, flexible model for building cloud-style applications. So let's illustrate some of those concepts. Go back to the EC2 environment, which we'd already set up. Customers, address spaces in the traditional way. Another customer comes along and deploys a VPC. Again, a VPC is a logical construct. So what's going to happen is their instances will show up in the Amazon cloud, running alongside, if you will, the existing instances. But from a networking perspective, they're isolated. They're sort of alone. And what happens is they get their own IP addresses within this VPC. I've got two availability zones illustrated here. And the VPC can span multiple availability zones. It doesn't span regions, but it's a regional concept. We can talk about more later about ways in which you can do cross-region things, but the VPC itself is a single region. And then you assign IP addresses to your instances. This is your assignments, not the networking stack that we run. And once those assignments are made, you begin to see there's a logical pattern here. Essentially, what I've done is created 3 subnets. 2 in one availability zone, 1 in another availability zone. And this is now my private enclave, and with automatic routing amongst these subnets. I can ACL the subnets, so I can put rules on the subnets, network rules, which give access control based on the standard things you're used to, addresses, site ranges, and so forth, ports, port values. And those are enforced. They're stateless, so you can have a separate set of rules for ingress, separate set of rules for egress. And that's on top of security groups and on top of the routing. So now basically one of the themes you're going to pick up here is there's now 3 kinds of control flow that you have instead of 1. You used to have security groups. Now you have subnets and routing. You have ACLs on subnets. And you have security groups still. All right? Now, you can do some additional things. You can add a virtual private gateway to your VPC, which is, again, sort of a logical construct, but it's a place where packet flow will be enabled under the right circumstances. That VPC, that virtual private gateway can have a corresponding customer gateway, which you can configure. That corresponds to a real router or something on the outside which you want to connect to. It can also correspond to another EC2 environment, which we'll get to in a second. And then you create a VPN tunnel using IPsec, standard technology that you're accustomed to. And this enables you now to have a fully private networking enclave in the public cloud. And you can add an internet gateway, as we mentioned, and directly access the cloud or the internet from within the VPC. Again, using the more traditional approach with EIPs, either on each instance or through a NATed instance, NatPad instance, so that all of your servers can go out through a single address if you like. And this gives you a great deal of flexibility. So here are some of the enhancements for the security environment and the isolation. Mentioned these already. 3 really critical things. You have control over network topology and routing. You have control over ACLs on subnets. And you have a number of enhancements to security groups. So what are those enhancements? First of all, egress control. So in VPC, you can now control packet flow or connection initiation, shall we say, out of the instance as well as in. You can reassign security groups dynamically during the lifetime of an instance, including running instances. You can have multiple security groups simultaneously, and there's a bit richer protocol support. You have some ability to choose some of the more low-level IP protocol types when you write your rules. And all these things, and I mentioned before, multiple interfaces per instance is an option. And all these things now can also be coupled with VPN technology to create a private interconnect between your on-premises environment and the cloud. There's one other capability that's associated with VPC. It's not technically a VPC feature, but from a kind of security design and business model perspective, we've made this association, and that is the notion of dedicated instances. Does anybody know what a dedicated instance is in Amazon? Anybody raise your hand? Yeah, a bit of an obscure feature. It's actually a little expensive because we're normally very inexpensive. We hope you feel the same way. Dedicated instance is the ability to tell Amazon, whatever you do with my virtual machine, I want you to run it on a piece of hardware where no other customer is running a virtual machine. So you get essentially isolated tenancy. It doesn't mean that only one VM is running there, but if there are other virtual machines running on that physical instance, they're yours. So it's a way of telling us a kind of placement model, which essentially is reserve some hardware for me. Now you may ask, why would someone want that? Well, for the most security cautious folks out there, there is a theoretical security issue called the cross-hypervisor attack, what have you. There's different names for this concept. It's been theoretically demonstrated as a possibility. Anybody that kind of knows how hypervisors work recognizes, yeah, if the hypervisor has a bug, you might be able to exploit that bug. And so, although I don't know of any in the wild exploits of this type, it's a theoretical issue. And if you want to protect against that issue and so make it so that no other tenant can somehow take advantage of this theoretical possibility, you can actually tell Amazon to allocate your virtual machines onto hardware that we've pre-allocated for just your tenancy and no one else's. Now, that's costly from our perspective, to reserve a bunch of gear, which we try not to do, right? As much as possible, sharing and pooling, but isolation and logical isolation. So there's a fee for this, which is relatively high. I think it's $10 per hour per AZ. Now that's a lot if you only have a few instances. If you have thousands of instances, it's noise. So in between, it's kind of becomes sort of moderately expensive. So just be aware of that feature. It's only available inside of VPC because we figured, you know what, if you're that concerned about security and these theoretical attacks, you're not going to want to be in the traditional networking environment. You're going to want to be in isolated networking. So it's a kind of feature of VPC, if you will. Now, on to my second demo. Now, this is where we have some audience participation. I'm going to actually show you an example of how you could use VPC, create a VPN tunnel, and be logically inside of VPC using completely private addressing, using a little bit of magic here. So what I've done is I've created there's a really nice security appliance, a virtual appliance available in our cloud, available also as real hardware from Astaro. They have this thing called the Astaro Security Gateway. Very cool technology. It's available as a virtual appliance, so it runs in EC2. One of its cool features is an interesting termination device called a RED. It's called a remote Ethernet device. And I have a RED sitting right here. You see this little guy right there? I'll lift it up here. So a RED, the bottom box, is a layer 2 over layer 3 tunneling device. So when you do an ARP on that guy, or any other low-level MAC level thing, that will show up on the other end of a tunnel in essentially the LAN on the other side. So this creates some really interesting types of capabilities. So basically what I've got here is we are on a LAN. Those of you who want to take the challenge, I'll plug in my wireless here. And if you'll see a little wireless, and the SSID is there on the screen, AWS VPC access. If you bind to that guy and tell me what your IP address is, I predict that it's going to be 10.3.0 something. And what you're doing is you're pulling a DHCP address from an EC2 instance, which is running the Astaro gateway, and is bound by a VPN tunnel into a VPC that I'm operating right now inside the cloud. So I'll do a demo, which is, again, as I mentioned, screencast, but you can follow along and do some of these same operations if you're bold. So first, here's my environment. I'll show some instances running. Again, I'll use Windows servers. That makes the visualization easy. And I'll do a series of operations kind of showing some of the VPC capabilities and tricks. Again, you can try some of these if you want on your laptop, because these should be there running, as far as I know, last time I checked, which was not too long ago. So what I have here is I've got some domain controllers. I've got some forensics boxes. We'll get to that on our last demo. And I've got 3 web servers. That's what we're going to focus on for purposes of this demonstration, each in 3 different availability zones. Those web servers are behind an elastic load balancer, which is showing healthy. If I connect to the ELB, which is this address you see in the corner there in the main address bar, it's going to hit one of those instances. But because I have elastic IPs, I'm cheating for the moment. I can actually hit the actual individual web server. So web server 1 resolves, web server 2 resolves, web server 3 resolves. And you can see the slightly different content of the 3 web servers. And just to prove that this is real, we'll go to the individual instances running IIS and Windows. We'll update those guys. You'll notice that I've got an auto refresh page, and as soon as I update the content of the web site, you'll see a slight change as I add an exclamation point with my little Notepad++ editor there. Now, if you go back to the main page, pulling from the ELB, you'll see those changes will be manifested as well. So both the main real website, which is behind an elastic load balancer, plus these point-to-point things I've done are showing the change. So this is the situation. Now we're going to get a little bit more real. Now, what you normally do in an EC2 world would be you'd isolate those web servers by writing a security group rule. Like you'd say, I want port 80 to be available for those instances only from the load balancer. So you'd pick the ELB security group. You'd assign a port 80 and maybe a port 443. You delete that crazy all thing that I have there, which is highly insecure. And now you'd be protected, so you'd be locked down. Only the ELB could talk to those web servers. But I'm not going to do that. I'm going to do something else. I'm going to delete the EIPs, the elastic IPs of those web servers, okay? One by one. Now, unlike classic EC2 networking, these web servers now are inaccessible from the internet, from the public internet. We've just wiped out the one way they were connected, which was through the EIP. So if I go to refresh, you'll notice the main website is fine, but my direct connections, you notice the little slowly spinning thing that Chrome puts up when it's unhappy. And so those refreshes are not working. So I've basically cut off my networking. I've also cut off my networking in another way because my RDP sessions are now dead. So I can't connect to those web servers anymore, and pretty soon you'll see that those screens will go gray, but in the meantime, my mouse clicks don't do anything. Those websites have timed out. Now we'll go to my Astaro gateway, and we'll show how we're creating this tunnel. So within that virtual instance, which is running in EC2, I've got a site-to-site VPN tunnel with my VPC, where the web servers are running. I also have a red connected. It's this red right here. Is anybody even brave enough to bind to this thing? And do you see the DHCP address? Anybody raise your hand? Boy, there's no one very bold. You got it, OK. Is it working? Can you ping inside there and so forth? Great. So now my timed out RDP sessions are going to refresh, because I've actually done split brain DNS, and I've created an internal DNS namespace that's the same as my external one. So even though I've got a completely different addressing, I'm going to rebind these things automatically. Because now since I joined this red LAN, red-based LAN, I'm now inside. Okay, the workstation that I'm demoing on is inside the VPC from a networking perspective. So now when I hit refresh on these, again, 3 web servers, the refresh works. Why? Because I'm inside the private address space. Even the Astaro gateway has the same DNS name, even though it has a different IP address now, and I'm able to go ahead and operate on that. Now, one other thing that I want to show just quickly is the DHCP that's being issued to you, those of you who are bold enough to bind to my little device here in real time. You're going to get DHCP from that device, and you'll be inside my VPC. Notice the difference between the trace route, okay, the trace route before, when I had a public address associated with web server 1, and I did a trace route, and I found, kind of a normal thing from a New York City office building to EC2. But now, when I do a trace route to the very same DNS name, which again I've reconfigured for internal, you'll see a very different route. It's going to go to 10.3, which is its gateway. You'll see the internal IPsec address, the 169, is inside the tunnel. And then on the other side of the tunnel, which we'll click back to in a second. And by the way, my local IP address of my workstation, which was previously 138, now it's an EC2 address, because now that's my gateway to the world. And just to finish the trace route, notice the difference in routes between being in the outside world and now the inside world, pinging my web server, which is this 10.1 address. So that's a demonstration of both a bunch of VPC features and also the ability to create completely private networking models in the cloud. So we mentioned some of these, but we'll begin to summarize common use cases. We have the ability to mix public and private resources in a more controlled way. A very common use case will be things like DMZ subnet, a subnet that's accessible from both the outside but also the inside. And the packet flow limited from the outside world limited to that subnet, and then a private control backplane typically on another subnet. You can multi-home your hosts on those two, or you can use security groups to get some of the same effects. Any workloads that expect fixed IP addresses, you saw that I maybe mentioned in passing, I've got a couple Active Directory servers running in my VPC. And those guys are happy because both DNS and AD really don't like their addresses to change, and no one else likes that either. None of the other Windows boxes or Linux boxes in there are relying on them. You can have, as I mentioned, multiple network cards, virtual network cards now. And really, one important value proposition, this matters a lot in the customer base that I work with in the public sector, is this idea of a private enclave of networking, extending your private networks into the cloud. Make your cloud hosts accessible without using VPN software, without using L2TP or some kind of tunneling on the clients. It just becomes part of your private network. You don't have to change your addressing scheme in order to make this work. You essentially match your addressing scheme between the virtual network you build in the cloud versus the ones you have on premise. And another interesting element to this is, of course, optional, but you can make it so that all of the outbound packets from the cloud, the egress model is through the corporate network, through the agency network, and out. So this enables you, if you have a certain threat model and a certain type of gear that you have, what have you, you've got an on-premises networking world that you're very happy with and you don't really want to change in terms of especially egress, which is a big concern for a lot of companies and agencies. That can remain the same because the cloud network is an extension of your private network, and its egress is the same as your existing egress, and your devices and your security models remain unchanged as the packets flow. Now, we have a bunch of rich capabilities in VPC. Some of our services have had to be modified and enhanced in order to really take full advantage of VPC. And a great deal of those enhancements have occurred. So things like ELB, auto-scaling, CloudWatch, the things you're accustomed to using in EC2 are available and work great in the VPC world. The relational database service now, RDS, has the ability to essentially create its own private subnet where the managed instances run. And then it actually uses the ENI feature to essentially put a network card, a virtual network card, inside your subnet in order to attach to this managed service. It's currently limited right now for various reasons to the MySQL engine, but you'll see that change so that all the RDS types will support that direct connection as opposed to, you can always get to them, of course, through the public side. But for like fully private addressing, that's now available. Elastic MapReduce has been enhanced, so you can run your Hadoop cluster in a completely private range, and the right things will happen there. CloudFormation has a bunch of now tooling that enables you to work well inside of VPCs, and that will continue to be enhanced and improved over time. There are many others of our services like that, and of course more to come. Now, it is the case that certain what I'll call black box services, like S3, where you just call an endpoint, it does work for you, returns is where you're very much removed from the implementation. Those endpoints are still public endpoints. That doesn't mean you go on the internet, but it means you go onto the public side of the Amazon network in order to reach those endpoints. And you can do that as you do today. So one last topic and then one last demo as we begin to wind down here. DirectConnect. DirectConnect is a related feature. It doesn't require that you use VPC, but people often use the two together. This is the ability to have private interconnect to the Amazon cloud. So you can actually now provision through a set of partners, telecom providers of various groups. You can literally run a optical cable from their cage to our cage in certain data center locations. And you can create these 1 gigabit or 10 gigabit interconnects so that your access to the cloud is completely private. It has two benefits. One is the kind of security and isolation benefit, sort of obvious, although VPN tunnels are pretty safe, but still, if you really want to be super careful and have nothing to do with the public internet when it comes to reaching the cloud, you can do that. The other is performance. You can basically, if you, working with your provider, can get very high connection speeds adjacent to us, if you will, logically adjacent, then you can just jack in and have that same very high-speed interconnect directly to the edge network of the Amazon cloud. And you're now removed from whatever variability that the public internet might be giving you when you do cloud access. Now, it's a nice companion technology for VPC because what we can do on the DirectConnect is we can do VLAN tagging, traditional hardware-style 802.11 type virtualization. And the VLAN tags can correspond to different VPCs. So you can actually have traffic over that one interconnect going into one or more VPCs. And even with the right permissioning, multiple tenants can share a DirectConnect and use VLAN tagging to reach their different tenancies within the cloud. So one last demo, and then we'll have time for questions and answers. I'm going to introduce virtually a customer who was unfortunately not able to be here. And then I'll talk through the demo. Whoops, something's not working here. Start my video.
Hello, my name is Kawaja Shams, and I'm from the NASA Jet Propulsion Laboratory, the premier NASA Center for Unmanned Exploration of Space. We have found cloud computing to be a game changer that has enabled scientists and engineers to rapidly process information and get results faster than ever. JPL has heavily invested in ensuring secure, effective, and compliant utilization of this promising technology. Cloud computing poses a key IT security challenge with forensic analysis and auditing in case of a breach. Within a physical on-premise network, we are able to isolate a potentially infected machine by simply disconnecting the wire and allowing a security expert to perform forensics on it. How can we accomplish the same capability in the cloud? At JPL, we worked closely with Mark Ryland from the Amazon Public Sector team to develop an instance isolation technique for the machines in our VPC using the elastic network interfaces. At this point, I'm going to hand this demo over to Mark Ryland, who will take you through the entire process of forensic-driven isolation, based on the techniques we have jointly developed.
So, of course, we can't do full justice to this, but we'll do the 4-minute version. So here's an email you don't want to get, and I really got this from Amazon. One of my instances was doing an unusual amount of port 25 outbound traffic. And the continuous monitoring systems that we run noticed that and said, doesn't look good. Unless you're a spammer, you probably don't want to be doing this. It's an indication of malware. Now, it turned out there was a valid explanation. But with that type of background, now let's set up this scenario. We have basically a VPC subnet where we have a web server, which is our potentially infected host, and we have a workstation, which is what we're going to use to investigate that host. We also have a completely isolated subnet. So our first step in this scenario is going to be to isolate the machine. We're going to put a security group on that machine that says no packets in, no packets out. First step, okay? In the actual demo, I'm going to cheat and do that second because I want to be able to show something happening there. But that would be that's the model that we've developed. So once that machine's isolated, now we have in place an existing subnet which is created. It's a forensic subnet. That subnet has ACLs on it so that only members of the subnet can send packets to each other. No packets can get in or out of that subnet. And what we do is we attach these elastic network interfaces, which are sitting there ready for this exact purpose, to those instances, and on we go. So let's walk through that scenario. So first of all, again, we've seen this setup before. I've got 3 web servers. I've got these 3 workstations. Those are the 3 web servers. They're sitting behind a load balancer. Check out the load balancer just to show you that the instances are there. We've got 3 healthy instances. And you'll see that change when we take one of these instances out of the rotation in a moment. We have a very quick health check, so it leaves the rotation quickly. It's a little unrealistic, but hey, it's the demo, right? Here are our subnets. And you'll notice that there are these 3 subnets in the 200 range there in the 3rd octet, one in each of our availability zones. These subnets normally don't do anything. They just sit there waiting for this forensics investigation. And on those subnets are some elastic network interfaces waiting also. Look at the ACLs on these subnets. They're deny all ACLs. So there's no packets that can flow into the subnet and no packets that can flow out of the subnet. Only machines on the subnet can communicate with each other. And again, those are the 3 subnets that have essentially this walled off environment. Now we're going to go look at our security groups. We have a special security group for forensics investigation, which we'll call the forensics target, FT. And what that does is it allows all the traffic to come inbound from another security group, that one that ends in 412. Let's look at that one now. That's the forensic source security group. It allows no inbound traffic, but it does allow all outbound traffic to the target security group, which is the security group we'll use on the potentially infected host. Now what we're going to do is, and here's where I'm going to cheat. Before we isolate that web server, I'm going to show you the binding of that of the ENI, the elastic network interface, to that web server. So let's do that. If you keep your eyes on the little Windows screens off to the right there, we're going to first take an ENI, which is sitting there waiting, virtually attached to that subnet. We're going to attach it to our investigation machine. Keep an eye on the Windows over there. It's a little plug-and-play magic will run, and boom, you'll have a second virtual interface now on that instance. We'll do the same on the web server, the one we're worried about. Click Attach. Second goes by, you'll get yourself a second connection there. Now we'll do, in kind of reverse order, a critical thing, which is we're going to change the security group on the main network interface of that web server to isolate. And the isolate security group stops all packet flow. So now the only packets that can come and go from that isolated machine are from other machines protected and cabined off, sitting on that private isolated subnet. Just to show that that server's out of the rotation, you'll notice that when we hit the load balancer, one doesn't show up. If you look at the health check on ELB and the status You'll notice that there's only 2 of the 3 instances are available, so that one's gone. It's unavailable. It's also gone in the sense now that I can't connect to it with RDP, so it's dead. But if I go to this multi-homed server, it can still, it'll update the existing web servers fine. But interestingly now, if I use the completely private cabined off IP address of the web server, I can still reach it. And that's the only machine in the world that can actually get a packet to or from the machine that I'm concerned about. And I can not only get packets there, I can get all kinds of packets, so I can ping that machine, and it'll respond. And I can even use, I'll do like a Windows DIR on that and see the C drive. So that shows you how I have this now forensics investigation machine, which is able to do a cloud investigation of a machine whose security may have been compromised. So that's the end of my talk. I've got time, I think, a little bit of time for questions. Any questions from the audience? Yes? Mm-hmm. Yeah, repeat the question. So what about overlapping private IP space? The IP spaces of each tenancy and of actually each VPC, because a tenant can have multiple VPCs, are completely segregated from one another. So there's no chance of collision. Essentially what we've done is created a virtual overlay that allows you to have your own addresses, and you can have your own set of those, or other tenants can have theirs. And really, if you can think about it, this is a way to deal with the pooling problem in a standard EC2. One of the reasons why you can't keep addresses for a long time is because this is a shared resource. And so you have this problem that if everybody wants to grab some of that shared resource, then over time you'll get fragmentation, you'll have garbage collection issues and so forth. But by going to the VPC model, we allow everyone to have their own set of addresses, which is up to them to manage. And getting in and out, of course, you have to, when you reach the outside world, you're going to have to do some thinking about how that works. But the exact problem that you mentioned is completely gone in the VPC world. There's no chance of address collisions because of the isolation of the VPC itself. Yes?
As far as the VPC having single points of failure, that the normal cloud, maybe the internet gateway or the NAT PAT device, how do people generally deal with that?
The internet gateway is a virtual logical capability that it's not a single point of failure. So you're not going to have a problem with that. The NAT device, which we currently support, is an EC2 instance, so it has the possibility of not being available. Some of our customers have used ENIs to solve this problem. They've actually created multiple redundant NAT devices, and they ping those periodically, and if one of them is having a problem, they just fail over to another one using this elastic network interface. In the future, you may see us make a more virtual and dynamical solution for that problem. It's not going to be bound to a particular EC2 instance, but that's how people are dealing with the question of reliability today. One more question?
I am in 3 regions, Amazon.
Yes.
And currently, I'm not on VPC. I actually want to move to VPC.
Right.
The fixed IPs and so forth. So I have to actually expose the public addresses of one region and add it to the security group of another region in order to be able to
Right.
get data. Is Amazon ever going to do something I can just take the name of the other region's security groups, I could add it to my security group, VPC or regular EC2? That would be very helpful.
Yeah, to summarize a great question and comment, why can't I have interoperability across regions and in between EC2 classic networking and VPC in terms of my security groups as named objects that I can write rules about? Great feature suggestion. Stay tuned. It's a really good idea. Thank you very much for your time.